laser, laser light from diamonds. See if we can make it layers in some other colors. Maybe not. Maybe it just wants to laze yellow. Oh, there we go. Here's a pinky orange. Cool. Well, that's unusual, huh? Very unusual color. Lasers don't usually blaze in pink and orange and blue. Isn't that cool? So I wonder if I can get it to laze over there. That's really cool, man. That is a really nice one. Alright, let's shut the light off and see what happens in ultraviolet. There's no other light here. My wife's light is over on the other side of the room, and I can't even see it from where I'm sitting. So all those colors are coming off of this diamond from ultraviolet light. Isn't that something? I didn't know it did that. But I think it has to do with the titanium coating on the back. Rather than the diamond itself. I don't think diamonds actually do colors like that without the... I mean, they do colors without a back, but not this one. This is just a clear diamond. The coating on the back creates a thin film, and they make colors like an oil slick on water, right? The little layers half the size of the wavelength of visible light, and that breaks light into its component colors with kind of a greeny purple sort of spectrum because of that thin film, and you can see that a little bit. It's more obvious on the clearer ones. I have one here. Maybe not. Anyway, what we see in many of these is a blue glow, and this is not actually like blue in there, it's just yellow. And when I look at the light, there it's just clear. It's just clear. And that's because the planes of cleavage create the color. It bounces between two layers, and it's exactly that shade of yellow light. That wavelength of light is the distance between the unit cells of the diamond crystal. And this was cut to look like a quartz crystal because people think they're quartz. But they're not. Diamond forms in a cubic hexagonal symmetry. So it has a corner like this where there's three even axes. Kind of looks like the corner of a box or something. Maybe it probably goes this way. And one of these, this has been cleaned up, so they're not usually so even. And they have some very distinctive crystallization habits that are easily recognized, but the cubic hexagonal means it's cubic in this direction, and when I rotate it 90 degrees, it's hexagonal. It's got 6 sides. Hexagonal means it's got 2 even axes, like bump and bump. They're the same distance across, here and here, or here, here and one of these. And so it's even. And one long axis, like this. Diamonds are cubic hexagonal, and that 90 degrees out is part of the structure of the atomic structure of the crystal, and the stacking order of the atoms inside the crystal. They are as close together as they can be. That's what face-centered means. And they're 10 on the Mohs scale of hardness. Quartz is only 7. So, like, this is a piece of glass. And, oh boy, I better put this down. Alright, so what I did was held my bottle of ginger ale, hitting the hard stuff again, and I made a scratch on it. This is silicon dioxide. In its amorphous form, glass, it's only 5.5, like an opal. Right? 5.5. And then my carbon crystals scratch it easily. Diamonds are not rare. They're not hard to find. These little things come out of the Ganges in large quantities, obviously, and I bought these, I think, for, I don't know, $10 or something for a kilo of them. And you know, they're really cool to look at because they're so clear, and they do things like make rainbows along the planes of cleavage. So you know, they make nice decorations. I can also make them glow. This stuff fell today on my junk pile and got dirty. But they are beautiful, and they've got a property that only diamonds have, and that's they are 10 on the Mohs scale of hardness, and that's why they don't have any scratches. Look at that. These came out of the river this way. They rolled and tumbled down from wherever they came from, and they are scratch free. And you can see how clear they are. Nothing else is as clear as a diamond because diamond has double covalent bonds, and those bonds are what allow light to pass through without resistance. Because light is a magnetic energy, and they are superconductors for magnetic energy and heat. So I can hold this in my hand, cut it, polish it, drill it with a hole saw, a big thing, and hold it in my hand without water. It doesn't get hot because of that superconductor property. Now, why do you think De Beers and all of that would not want us to know that? Because you know what? All the gemologists in the world are going to say, oh, that's not a diamond, because they had 5 hours of classes on the science behind diamonds. Cost them a bunch of money, and they've invested a lot of money into selling you little tiny diamonds at very big prices, even though you can buy them on eBay for a few dollars if you know what you're looking for. I bought these rough and cut this one a few years ago as a cabochon to see what it looked like, and these are unusual because they have like a fractal pattern on this side. I have 4 of them, I think, maybe 5 of them, uncut other than this one. And so I've been playing with these a while. I really enjoy them, and I've been chasing opal most of my life like this. And I found out that this Ethiopian opal that the Lightning Ridge black opal miners were so up in arms about because they thought it was dyed. Well, it's not dyed. And in fact, it's 10 on the Mohs scale of hardness. It's not even opal. Opal is only 5.5, like my piece of glass. And so if I take a known diamond, and diamonds have the sparkles around the periphery, okay, and that's the quickest, easiest optical test you can give it. If it sparkles around the outside, it's because the planes of cleavage are following the angle of the pavilion, and they're opening outwards and catching the light, and they direct the light around the outside. And the inside is so clear you can see the bottom, not through the hemp seed oil, unfortunately. You can see the bottom as though it were there was nothing in between. Diamonds are also really, really reflective. Okay? And they're really, really hard, and if I try to scratch my opal here, it doesn't scratch. It doesn't scratch. It's 10 on the Mohs scale of hardness. I think that this stuff is melted AUPT. This stuff forms in fault lines and is associated with volcanic ash. Volcanic ash is mostly AUPT. That's why it's got that gold color. If I blow it up a little more, you'll be able to see some cubic structure in there. Yeah, see, there's planes of cleavage. That's why things line up in rows and columns there. And they do so in a couple of different directions, because the planes of cleavage cross. And AUPT is also formed in the cubic hexagonal system. Face-centered cubic hexagonal. It's as close together as they can, those atoms are, as they can possibly be. And on this side, we've got this. They broke this open with a tool and whacked it, and you see like a little cone of compression right here, like arrowhead making or something, right? But they break along those planes of cleavage. That's what those lines are caused by. And they break very glass-like, right? Because I think they've been melted in subsequent volcanic activity. They're associated with what we call secondary mineralization. And they form in fault lines. You find them in fault lines. And that's where you find AUPT too. And there it is, AUPT. And I think the size of the unit cell here of this AUPT was the right size when it melted. They didn't melt. They line up in perfect little rows and columns trying to get back together to be a crystal. And so there's a very orderly arrangement of the unit cells that look like kind of spheres if you look at them in old-fashioned electron microscopes. I know that sounds kind of like an oxymoron, but we've had electron microscopes since 1964, and opal was one of the first things they looked at. And people went, ooh, because they could see these spheres all lined up in perfect rows and columns in face-centered cubic hexagonal arrangement. And so if you look in the books, that's what it's going to tell you. Or at least the face-centered hexagonal. Opal is supposed to be amorphous. And it is. That's why it breaks like glass, right? This it's called conchoidal breakage. Shell-like. And you can see it's kind of dished out, right? My finger sits in there because it's dished out. They popped it up here, and there's a lines going away from that where that force broke across there. And they broke it open so that they could see what was inside of it. Because you don't know from the outside, right? Unless it's got something showing, and this doesn't. So there it is, a piece of Ethiopian melted AUPT. And it formed into a glass because of the high temperature. It has to be up over 1768 degrees to melt platinum. And that's what happened here. In the KT extinction event, there was a nuclear holocaust that wiped out the whole planet in a few minutes. And that nuclear fusion is sufficient to melt these, and these probably were on the surface as little like dirt clods in the volcanic ash, and it rolled along, bump, 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 because it was round, right? It didn't start out half like this. It started out round like a thunder egg. But that's what it is. It's melted AUPT. And in a fault line, when that happened, I don't know. I'm still trying to figure it out. I'm still trying to figure out the way that the events happen. And when I find out, I'll let you know. In the meantime, it's not really opal, it's something else.